Swayam Prabha. Digital India. Educated India.
Okay, so what we have discussed so far was basically TWI models that describe the end-to-end distance squared averaged of a polymer chain. We did for a flexible chain models, and then we did for a semi-flexible chain in the previous class. So now I want to think beyond the mean of the squared end-to-end distance. Let's say like how the distribution of the end-to-end distance looks like. And using that, what I want to ultimately build is the notion of an elastic energy of a polymer chain. So first we will discuss like how the probability of conformations vary, and then finally how can we associate that with the elastic energy of a polymer chain, and that we will use in the further components of this course. Okay. So let me first discuss the idea of a thing that I will use, that is called probability density . So most of you, for example, know what is a probability. For example, if I am doing like a coin toss, and if I am being like unbiased in terms of how I am tossing it, then the probability of having a head or a tail is simply the same, and they are equal to 1 by 2. So in this particular case, there are only two outcomes of the experiment. Either it is a head or a tail. So in that case, we can say that the random variable takes two values, head or tail, or I can say, if I say head is a number +1 and tail refers to some number like -1, then it can take values like +1 or -1. Okay. So this is when we use the idea of probability. The probability density comes into picture when the random variable can take values in a continuous domain. For example, when we talk about the end-to-end distance, then the end-to-end distance can really vary from, I would say, 0 to higher values, let us say 10 to the power 6 or what not. Actually, we talk about the end-to-end distance, then we talk about also the sign of it. So it can vary from minus of 10 to the power 6 to 10 to the power +6, thinking that the chains are very large, and it is like varying continuously. That means that we can take any value in this particular domain, not really certain discrete values there. So in that case, what we talk about is a probability density that is defined in this particular way, that PRE multiplied by DRE is the probability that RE is between some value RE and RE plus DRE. Okay. And in that case, this is what I will call a probability density. Okay. That is one idea that is important for us. The other idea is like, unlike the coin toss example, where there is only one experiment being conducted which has an outcome head or tail, in the case of a polymer chain, if we think in terms of the TWI model, then the random variable is not the end-to-end distance vector, the random variable is my bond vectors. So let us say if I think of a freely jointed chain, what I am actually varying are the bond vectors which I represent like B1, B2, B3 and so on. So, in the end what I am looking at is essentially a sum of random variables, each of which can vary and each of which has certain range. So, we looked at the ensemble average of that was equal to 0, and we looked at the correlations of that, and that varied for different chain models, but for this particular model it was equal to something like V square when I is equal to j. Okay. So, we will use these two ideas. We will talk about probability density of having a chain end to end distance between RE and RE plus DRE. Here when we say the end to end distance, we also account for its sign. That means that negative values of RE are not same as positive values of RE. And the other idea we will use is we are not looking at one random variable, but a sum of random variables that is giving rise to the end to end distance vector. Okay. So, with this now I want to use the simplest model that we derived, the one dimensional random walk, because in that case we are only moving around one dimension. That really simplifies our analysis. In that case the end to end distance is only along one dimension, and we can then extend the idea to higher dimensions or actual 3 dimensions, as in the case of a freely jointed chain. Okay. So, let us go back to the 1D random walk, and now the question is not that what will be the mean square end to end displacement or distance of the drunkard. What we are interested in, like what is the probability that he moves 5 steps to the left or 5 steps to the right after so many steps. Okay. So, other way to think about it is we are trying to find whether he will reach his home in certain number of steps, provided the home is around certain number of steps away, let us say 10 steps away. So, let us say if he starts from here and he wants to go to here and he made say 20 or 30 steps, what is the probability that he will get home in that particular step? That will correspond to having certain end to end distance RE after let us say m steps, and we talk about the probability of having that. Okay. So, we are doing it for the discrete case. In this case we do not talk about probability density, but we will soon go to the limit when the number of steps become very large, and then we have a continuous distribution. So, right now this is the probability that the drunkard moves RE steps to the right after m steps. Okay. And just for simplicity we will take B is equal to 1, that is at every instant he can move 1 unit in the left or 1 unit in the right, and that would be equally probable. That means that at every time, irrespective of how he moved in the previous step, he can move either to the left 1 unit or right 1 unit. Okay. So, let us say in these m steps he moves m plus steps to right and m minus steps to left then for this to be true, for the distance travelled to be equal to R e to the right, what we should have is m plus minus m minus must be equal to R e, because at every step he is moving like 1 unit. So, he moves like m plus steps total to the right and m minus steps total to the left. So, m plus minus m minus is a net distance travelled in the right direction. Now, since the total number of steps is m plus m minus is equal to m. So, if I solve these two equations, what I do get is m plus is equal to m plus R e by 2 and m minus is m minus R e by 2. So, now if I want to know how many ways there are in which he is making this particular combination of steps, then basically what it turns out is I can define a quantity W, that is the number of trajectories that give rise to end-to-end distance R e in m steps, that is the standard permutation problem, is m plus m minus factorial divided by m plus factorial m minus factorial. All we are doing here is, since every step can be to the right or to the left, so we can choose m plus steps out of the total m plus m minus steps. So, basically what we are doing is the combinatorial m plus m minus c m plus, and this is what we have done so far. Okay. So, now we will use the idea that both m plus and m minus has to be very large if I try to think of this model applied to a polymer chain, because the polymer chains has many steps. Okay. So, if I try to do that, the first thing I will do is I will use the relation that I have derived earlier. So, this is equal to now, one thing you can clearly see from here is, of course, for smaller values of m, this will be very easy to compute, but for larger value you try plugging in this into a calculator and you will soon find the numbers start become very huge. That means, if I try to do say 100 factorial already on a calculator, this becomes a very large number. Okay. And so, one thing is that they are difficult to compute, the other thing is that we can make certain approximations that will apply for larger values of m. So, the approximation we are going to apply goes like this. So, we are interested in the log of this value, and we will see like why this become useful. The log will go like log of m factorial minus ln of m plus R e by 2 factorial minus ln of m minus R e by 2 factorial, and then we will use what is known as the Stirling formula. But before that, let us try to simplify this particular relation. So, if I look at, for example, this term is equal to ln of m by 2 factorial, m by 2 plus 1, m by 2 plus 2, and so on until m by 2 plus Re by 2, and this I can write as ln of m by 2 factorial plus sum over some variable, say s is equal to 1 to Re by 2 . So, please do not confuse this s with the contour variable I used in the different class. This is really a variable going from 1 to Re by 2. And if the same thing I can do for this term, and let me do it on this side. So, ln of m minus Re by 2 factorial can be written as ln of m by 2 factorial divided by m by 2 minus Re by 2 plus 1 m by 2 minus Re by 2 plus 2, and so on until m by 2, which I can write as ln of m by 2 factorial minus of the sum m by 2 plus 1 minus s. Okay. So, now I will use these two relations that I have derived in here, and what I end up having is ln of W Rem is ln of m factorial minus 2 ln of m by 2 factorial plus minus s going from 1 to Re by 2, and then I have 2 log terms here. So, they form like a ratio . Okay. So, now what I can do, I can divide both the numerator and denominator by m by 2, and this becomes equal to s equal to 1 to Re by 2 1 plus 2 s by m divided by 1 plus 2 by m minus 2 s by m, and of course, there was a ln here in case we have forgotten the ln was present in this. Okay. So, now we can use again the idea of a Taylor series. So, we know 1 plus y, the ln of it is equal to y by Taylor series. In this case, we can use that because y equal to 2 s by m is small since m is large. Okay. So, if I do that, then this particular term become equal to which is equal to which I can write as okay. So, now this becomes a simple series which we know that summation of numbers, this becomes equal to R e by 2 multiplied by R e by 2 plus 1 divided by 2, and this is of course 2 by m. So, we are simply adding 1 R e by 2 times. So, we have this thing. We can do certain cancellations. So, we have the second term in the first expression is R e by m, that cancels with what we have here. So, what we are left with is R e square by 2 m. Okay. So, now the relation we started with gives me okay. So, now there is one further detail here. So, W is the number of confirmations that gives me an end to end distance of R e. So, if I talk about the probability of that to happen, the probability will be W divided by the total number of possible ways we can make a movement. So, the total number of ways or total number of possible trajectories must be equal to 2 to the power m, because at every step the drunkard can move either to the left or right. So, at every step there are 2 possible choices. So, if I take a power of 2 to the power m, we get the total number of trajectories. The probability for this to happen will be W so we can write ln of P R E m is equal to ln of m factorial minus 2 ln of m by 2 factorial minus R e square by 2 m and minus m of ln 2, that is simply the ln of 2 to the power m. Okay, so we will start from this particular expression that we have derived, and we will use the relation that is known as the Stirling approximation to get these factorial terms, and based on that we will derive the expression of probability distribution for the larger values of m in this case. Thank you. Factorial